Welcome everyone to the today's session. So this is a free lecture series in which we will be doing the tough topics of IIT JAM, CSIR Net, GATE, these kind of exams. Some topics are of JAM level, so this will directly help the BSc students and also MSc students because JAM syllabus entirely is also in GATE and Net. Some topics will be of GATE level or Net level. These will help BSc students if they are preparing for JEST exam or TIFR exam because those topics will directly come in these exams. So today, before I start the session, can anyone, one or two people confirm that can you hear me properly?
Yes,
Yes, sir.
sir.
Oh, thank you. So quantum mechanics. So before jumping to a very tough topic of quantum mechanics, let's understand what the quantum mechanics is. Let's have an understanding of quantum mechanics. Whenever a people teach quantum mechanics, they start by teaching direct notations or what is the wave function or so on, because they think that in this way it is better to have a give the feeling of quantum mechanics. But no, with the problem of one-dimensional infinite potential well, I will teach you what is quantum mechanics, and also your one very important topic will get covered. So let's start. So in quantum mechanics, every system, let's say you are describing some system. So to describe that system, you need to describe potential. Describe potential. So what are the quantum mechanical systems? First of all, let's say hydrogen atom. Okay, let's say electron in crystal, etc, etc. So hydrogen atom, if you want to describe the system which is hydrogen atom, you need quantum mechanic description. If you want to describe an electron which is present in a crystal and you want to study the motion of that electron or the behavior of the crystal, you need a quantum mechanic description, or we say that this is a quantum mechanical system. So in order to mathematically model the quantum mechanical system, you need to describe the potential. You need to define the potential. Okay. Potential means the force which is acted on the particles which are involved. Because we know that if you know the potential, you can find the force by a simple formula minus grad V. Okay. That is the reason why we need the potential so importantly. So in one dimensional infinite potential well, this is a very, very ideal situation of a potential. This kind of potential can never be uh, uh, realized in the real life situation. But this is a very good ideal situation, which can describe many physical systems like electron in a crystal. Try to understand how it can describe. So first, let's see what is one dimensional infinite potential well. For this system, the potential is zero inside some region which we call it as well. It is called it as well. It is also called region 2 or well. Okay, so potential is zero inside this well, means inside this small region from 0 to a, and the potential is infinite, means completely infinite outside this small region. So otherwise, for all other values of x, potential is infinite. Okay, this is the situation we have. Now this is very similar situation you can see in terms of electrons in a conductor. Let's try to see. You have an atom, you have a valence electron. Okay, we know that this valence electron is very loosely bounded with the nucleus. So the potential is almost zero. Potential is almost zero. But it cannot leave this atom until unless any external force is applied. So it cannot leave the potential. So in order to go outside it, some sort of need a huge amount of energy, which we can consider it as infinite energy. It is not at all the practical situation. It is not at all, because we do not need infinite energy to remove the valence electrons. But if we make sure that our electron will not go out in any situation, then we can assume that we need infinite energy to remove it. We can assume if it is given to us that electron will never leave the atom. So I'm just telling you that these kind of ideal situations can also be used to describe the actual problems, like electron in an conductor or electron in an insulator. You know, the valence electron of insulator cannot leave the your valence band. So these kind of situations we can model using the quantum mechanics. So now let's study this ideal situation. We have potential 0 within this region and we have infinite potential outside. What do we want to find? What we need to find? What we need to find? First of all, we are assuming that there is an electron inside this well or some particle inside this well. Let's not name that particle. So particle is inside. Particle is inside well. Now we want to know everything about this particle. Like, what is the energy of this? What is the energy? If I make the measurement of the energy of this particle, what energy will this particle will have? Similarly, momentum. Momentum. What will be the momentum of this particle? And other quantities like angular momentum can be there, and so on. There can be many things. But is a position, means if a particle is inside this well, where is it actually? Is it here? Is it here? Where is it? So that we also need to know. So position we also want to know. Okay, so all these things we want to know. Now comes the first very basic and very fundamental principle of quantum mechanics. So let's deal with it. Quantum mechanics says if you want to find out the everything about your system, then you just find the wave function of that system. Or in quantum mechanics, probability amplitude is a very new word you must have seen, probability amplitude, or simply called wave function. Okay, so probability amplitude is another name for wave function, or wave function can tell you about all the features of system, all the features of the system. So this is a quantum mechanical description. So how can it tell everything, and what is this probability amplitude? These are the two questions which should come to our mind. That what is this probability amplitude which can tell us everything about the system? And secondly, how it can tell us everything about the system? Okay, so let's deal with the first question. What is this wave function? What is this wave function? Okay, it's a very important, very important description, and very important that you have that clarity in mind. So wave function or probability amplitude, let's say PA, you need to remember that PA means probability amplitude, is actually complex functions. Okay, so they are complex functions in general, means they can also be real, but in general they are complex. They do not have any meaning of their own. No meaning of their own. There is no physical meaning of their own. But if we know them, we can find out other things like momentum and energy and so on. So this is a general description. There are some properties of the wave function. What kind of properties this wave function will have? So that is a different discussion. We will not do it today. That I will take a separate class. What are the properties of this wave function? So these two things you should remember, that it is actually a complex function, simple complex functions it could be. For example, sin x. So now many students think that sin x is actually a real function, but let me remind you that sin x is actually a complex function. Why? Because you know you can represent it like this. Okay, so now you can easily see it is a complex function. Similarly, cos x. and etc. These kind of functions can be the wave functions. Okay, and these, if I give you sin x, there is no meaning of it its own. So now moving forward, how to find this wave function? Okay, I will go to more deep analysis of this wave function as we will move along. So how to find it? How to find it? So that our very good scientist Erwin Schrödinger gave us the answer that how we can actually find this wave function. First of all, it is a one-dimensional problem. I'm saying that my potential here you can see is only along x-axis, means I'm only talking about x-axis right now. Okay, so I am dealing this entire problem in one dimensional. So my wave function will also be in one dimensional. Simple thing, because I am not taking x, y, and z direction. So how to find our very nice teacher, which is our nice scientist Erwin Schrödinger, gave one equation. Okay, like Newton gave one equation. This Newton gives us an equation that force equals to ma. Whatever is the force acting on, if you use this equation, you can find the acceleration of the particle. Okay, and if you know acceleration, you can find momentum. If you know momentum, you can find kinetic energy. If you know kinetic energy or speed or velocity, you can find angular momentum. So everything you can find. You just need this acceleration. You have the already have the mass. You know what is an external force acting. So Newton's equation did everything well in classical physics. Okay, and similar thing is Schrödinger's equation doing in quantum physics. Okay, so what is this Schrödinger equation? So the very simple equation I am going to tell you is, first we will begin with the actual Schrödinger equation, that is h cut phi equals to E. So very complex equation I have written. It may seem like a 4 words only, but it's actually a very complex equation. Let's break it down. Okay, so phi here is actually a eigen function or a wave function. Okay, wave function. I would say that you should not call it wave function. Either you should call it as energy eigenstate. Why we are calling it as energy eigenstate, I will just make it. H is an Hamiltonian operator. E is a value of energy, and again phi is again an energy eigenstate. So now comes the second principle of quantum mechanics. First principle we already discussed. Now second principle of quantum. What is this? In quantum mechanics, every observable is represented by an operator. For example, energy is represented by Hamiltonian operator. Okay, so this equation you clearly see every observable. What is observable? Observable is something which we can observe, which we can measure. For example, energy we measure, kinetic energy we can measure, or we can't. That is a kinetic energy, I'm not so sure, but energy we can measure. Okay, then we can measure angular momentum, we can measure the spin of the system, and so on. All these things which we can measure are actually represented by the operator. Okay, is represented by the operator. Okay, so now let's see what is this equation means. This equation means if you apply the operator h cut, which is actually an energy operator, to our state, it will give you the value of energy and this state back. Okay, so in a sort of thing, you are actually operating this operator on a system or your state phi. You are getting some energy value E and you are getting your state back. Okay, state back. So this is an operator. This is your state wave function. Okay, and this is your energy. which you are getting, and this is again you are getting your state back. Okay, so let's dig it down. So what is actually this H cut? So H cut is actually a kinetic energy operator plus the potential energy operator, because we know total energy is a sum of kinetic energy plus potential energy. Similarly, the operator H cut will also be the equivalent of kinetic energy plus the potential energy operator. What is kinetic energy operator? Kinetic energy operator is simply momentum operator square by 2m. You know this definition that kinetic energy is P square by 2. So kinetic energy operator will be uh, momentum energy operator squared by 2. Similarly, B operator is simply equals to the whatever the potential your system has. So whatever is a potential your system has, that is equal to your potential operator. That is the thing which you should remember. Now, what is this P operator? P operator also, you do not need to go into the derivation and find out. You just simply need, it is minus iota h cut d by dx. Okay. So this is, for the beginning, you should actually at least remember this thing, that this is your momentum operator. So what will be our Hamiltonian then? So just square it. If you square the momentum operator, you will get minus h cut square by 2m d square by d phi square dx square plus whatever is the potential. This is your Hamiltonian operator in all the situations. Okay, all the situations. Okay, now coming forward. So what will be our Schrödinger equation then? It will be minus h cut square by 2m d square phi by dx square plus v phi equals to e phi. Now mathematics is okay, but here I want to stop and tell you that what we are actually doing. Now it is a right point to see what we are actually doing. Okay, what is here phi here? It's very important. And what is E here? So let's say you have the potential well, you have the particle inside it. Okay, now this particle may take many energy values. It is not that only one energy is possible. It is very quite simple that if let's say you are in a room and you are in a very restricted room and you are moving, let's say you can move with any speed. So the speed which you will have will decide what is your energy. Similarly, the particle which is inside this well can have many energies. So for all the energies, let's say it will have the energy E1, it will have the energy E2, and so on, so on. So this equation tells us that when our system will have the energy E1, what will be the state of the system? What will be the state of the system? Okay, or let's say the state means how we are defining the state, that it means that when our particle has energy E1, our and our particle will have the state phi 1. When our particle has energy E2, our particle has a state phi 2. So this quantum mechanics completely solved the problem of either the electron is a wave or is a particle. How it's solved? It's a very funny thing. So it says that electron is neither particle, it's nor wave, it is a wave function. Okay, so not wave, okay, not particle. So what is it? It is a wave function. Oh, what are you saying? What is this wave function then? Quantum mechanics says, I'm sorry, this wave function has no meaning of itself. What kind of theory is this? It is the theory and you have to accept it. Okay, electron is not wave, it's not particle, it is a wave function. And this wave function, what is this? We can only find the things with this wave function, but this wave function itself has the no meaning. This is what quantum mechanics is. And how do you find this wave function? You solve the Schrödinger wave. Okay, now remember, Now remember, here phi1, phi2 are not the, every electron do not have the one wave function only. Okay, so if you are talking about energies, total energies, then your wave functions are phi1, phi2, then your states are phi1, phi2. Let's say you change the uh, your physical quantity. Let's say I now decide to measure momentum p1, p2. So when your electron has a momentum p1, quantum mechanics says it will have the state wave function delta 1. Okay, when it has a p2, it has a state delta 2. But okay, so for every physical quantity there are some states related to it which are called eigenstates. Eigenstates. So these are called momentum eigenstates. These are called energy eigenstates. That is why I was saying that you should remember that these are not, we should not call it actually wave functions. We should actually call it as energy eigenstates. Energy eigenstates. Okay, what is then wave function? That we will come to this. That everything energy eigenstates are also wave functions. But now for now, remember that these are actually energy eigenstates. And the Schrodinger wave equation, when you solve the Schrodinger wave equation I just defined, you get energy eigenstate. Many students get confused here. Even I was confused for very long time. So when you are measuring momentum, you are getting different functions, delta 1, delta 2. So when particle has momentum p1, it is in state delta 1. When it has momentum p2, it is in state delta 2. What is delta 1, delta 2? It is momentum eigenstate. So the problem comes that I just said you, if I know the phi1, phi2, I can measure everything. I can know momentum, I can know energy. But now I am saying if I'm talking about p1, p2, the functions are delta 1, delta 2. So it is a very big problem. But don't worry. If you actually know phi1, phi2, na, in the advanced quantum mechanics, which you do not know need in this lecture, you can actually find delta 1, delta 2 very easily. Okay. So if you know phi1, phi2, phi3, all things, you can find delta 1, delta 2 in them. And not just delta 1, delta 2. Let's say if you talk about angular momentums, if a particle has angular momentum, it will have the state, let's say chi 1. L2, it has a state chi 2. So you can, it is like then called angular momentum eigenstate. Okay, angular momentum eigenstate. So once you know the energy eigenstates, you can easily find momentum eigenstates. You can easily find angular momentum eigenstates, and so on. So I will just take a break of 10 seconds and know that is my voice still okay?
Yes, Bhaiya.
Okay. So let's recap till here because I have told you so much of quantum mechanics with the problem of infinite potential well that maybe you must have forgotten what we were doing. So we started. My screen is frozen. Can you see my screen moving?
No, भैया.
Okay. So just a second. Let the screen come. Okay. So now it is moving. Yeah. So what we started with is, so we described the one problem which is called one-dimensional infinite potential, and we tried to understand entire quantum mechanics. We said that this is a very ideal situation which can actually be modeled to explain many quantum systems like crystals and so on. Then we say it is a system in which potential is zero in some region and it is finite, infinite in other regions. Okay. So then we say that we want to solve this problem and question comes, but we actually want to solve, but we actually want to know. Then we said that we want to know all the physical quantities like energy, momentum, position, etc. of the particles inside this well. Okay, and I think the screen is moving very slow comparative with the what I'm saying. Okay, wait for 10 seconds. Okay, so now it's fine. Even the IAC Wi-Fi is lagging today. Okay, no problem in that. Screen is moving little bit slow, but not a problem. So we said that if we want to know all these things, we need to find the wave function. And then I told you that how to actually find the wave function, or actually find each and everything by starting with the Schrödinger equation. So then I told you that this is a Schrödinger equation. Actually, this is a time independent Schrödinger equation, not the Schrödinger equation itself, but time independent. There is no dependence of time. For now, for a moment, we have actually stopped the time. Schrödinger wave equation. We have actually stopped the time, and we are dealing with our system. So I said that if you solve this problem, the solution of this problem will give you the energy eigenstates. Energy eigenstates. And then I make a statement that if you know the energy eigenstates, you can actually find all the kind of eigenstates. For example, momentum eigenstates. For example, angular momentum eigenstates. And if you know energy eigenstates, you know the energy. What are the possible energies? If you know the momentum eigenstate, you know the possible momentum values which your particle has. So all we need to do is find the energy eigenstates. If in some situation in advanced quantum mechanics, sometimes it happens that you can't find energy eigenstates, but you can find momentum eigenstates. So that is also equally good. If you can find momentum eigenstates, even with that, you can find all other eigenstates. But for a basic quantum mechanics, we usually find energy eigenstates. Why? Because our scientist Schrödinger told us that how to find. They gave us the equation to find the energy eigenstates. So let's dig in. So then we described the all the terms in this energy eigenstates, and we said that this h cut is actually an operator. What is an operator? Then I defined one more statement that in quantum mechanics, every observable is represented by one operator. So similarly, the momentum will have some operator, energy will have some operator, and so on. Then we defined our Hamiltonian operator as a sum of kinetic energy operator plus potential. So if it is a sum of kinetic energy operator plus potential energy, then we need to define what is our potential energy operator. Potential energy operator is simply equal to potential energy. Whatever is the potential energy of the system, that is a potential energy operator. And what is the momentum operator? It is minus iota h cut d by dx. Very simple thing. And then through this, we was able to define the energy operator, which we also called as Hamiltonian. So we know the Hamiltonian now. So with all this quantum mechanical explanations, now then it's good time that we find the energy eigenstates. Actually we will solve this. So how we will do that? We have got this very beautiful equation. Okay. So now number one thing is that for a moment we just solve the problem for region number 2. Region number 2. What is this region number 2? The region number 2 is a place where potential is 0. Okay, we defined that the potential is 0 in the region number 2 between the well. So what will be our equation? Minus h cut square by 2m d square phi by dx square equals to E phi. Okay, so let's simplify it. Minus d square phi by dx square equals to minus 2me by h cut square phi. Okay, so I hope that all of you have a very basic understanding or knowledge of the differential equations. This differential equation is a very famous differential equation, and you can actually find the solution very easily. What is this differential equation? This is an harmonic or simple harmonic equation. Harmonic equation. Simple harmonic equation. Why? Because your double derivative depends upon your x or function. Okay. So double derivative of some function depends upon the negative of that function. Then you know that it is an equation of simple harmonic. Okay. Or in simple words, you can see that this is a double second order differential equation, second order ordinary differential equation with constant coefficients, with constant coefficients. So how do we solve this equation then? Try to remember the solution, the d square, okay, plus let's say this entire constant as omega square, or let's say k square. Give this, define this entire constant as k square. It's our choice, we can define anything. So d square phi plus k square phi equals to 0. So now we can easily see this, that d square plus k square equals to 0. This is how you solve that double derivative, second order differential equation. So what is d? D is actually plus minus iota k, plus minus iota k. So if d is plus minus iota k, then your solution is actually a e raised to power iota k plus b e raised to power minus iota, sorry, kx d raised to power minus iota kx. Or we can also write it as a sine kx, or we can also write it as a cos kx. All of these are possible values, but all of them do not make the physical sense. If you assume these three solutions, so it's a very important also. This was asked to me in the interview. In most of the books, you will see that derivation, they will directly say this is a solution of this differential equation. Absolutely right. If you put this phi in your equation is satisfied. But if you put this also, your equation will be satisfied. And if you put this also, your equation is satisfied. Then why we are neglecting this and this and only taking this? Why we are only taking sine? This is all actually a very important relevance here. Okay. And the answer to it is boundary conditions. In quantum mechanics, always remember that your answer will depend upon two things. Your state is defined by the two things. Number one, what your Schrodinger equation is giving, and number two, your boundary conditions. So moment, for a moment, before applying these boundary conditions, let's assume that all the three solutions are equally good. Okay, all the three solutions are for now equally good. And come to the case 2. Case 2 is when we are outside, means when our potential is infinite. Then without any hesitation, you can say your phi is 0. Your phi is 0. Means your wave function or your energy eigenstate is 0. Why? Because one Mr. called Born, he has a very nice explanation for one thing. When the people asked what is the physical meaning of wave function, Mr. Born came and said, phi has no physical meaning, but if you take the complex square of phi, means phi star into phi, then it is defined as probability or probability of existence, because phi was probability amplitude, and if you square it, it becomes probability. So there is a difference between probability amplitude and probability. Okay, so our Bone said phi is a probability amplitude and phi is actually a probability amplitude. This was also given by Born. Before that, no one was thinking of in terms of probability. And if you complex square it, you can write it like this. In easy terms, it is written like this. So if you complex square it, it defines the probability of existence. So at what value of x it will be, what is the probability of finding the particle at any particular x is defined by phi square. For example, let's say if I assume that my phi is a sine kx, then my phi square x is a square sine square kx. And if I want to know that what is the probability of finding the particle at x equals to a by 2, then I just simply need to insert this x equals to a by 2 and I will get that probability. So this was the entire interpretation of the Bohm about this wave function. So how is this useful to say that phi is 0? Because just think about it. Your potential is 0 outside the well. So if potential is 0 outside the well, it means you are experiencing infinite energy or infinite force. If you have infinite force acting upon it, what will be your energy? Infinite. Okay, your energy will also be infinite because you have the infinite. Because what is energy? Simply potential energy plus kinetic energy. Even if I assume that my kinetic energy is 0, even if I assume that, even then my energy will be infinite. And can any particle have infinite energy? Tell me, yes or no? Can any particle have infinite energy in this universe? Say yes, no.
No, sir.
No, sir, because it can't. Yeah, definitely. And if particle can't have infinite energy and our phi represents the probability of our particle to be there, then our particle can't be there outside. So if particle can't be outside, then phi must be 0 outside. All of you understand why phi is 0 outside? Tell me yes, no. Very quick. It's very important.
Yes, Bhaiya.
No, sir. Please repeat.
No, please repeat. Okay, thank you. So phi is representing your probability to exist outside. Not actually phi, but the phi square is actually representing your probability of being outside. So if a particle can't be outside, then the probability of existence of particle outside should also be 0. So if it should be 0, then our phi should be 0. Okay, so let's say there is some parameter a which defines that your particle will be outside or not. So if your particle cannot be outside, then this a should definitely be 0. So that is the reason why phi is 0 outside. Okay, so phi is 0 outside. The concept to know that why phi is 0, we actually defined the Bohm approximation also, or Bohm interpretation also. So one more quantum mechanical concept is done. Now, before I come to boundary condition, I want to explain two more concepts of quantum mechanics, because that is also very important, my friends. That is called the properties of our this very beautiful function called wave function. Okay, very beautiful function called wave function. So this phi must be continuous everywhere. Okay, everywhere. It is not possible ever in this universe that this phi is not continuous. If any function is not continuous, it cannot be wave function. Okay, it must be single valued everywhere. Single valued everywhere. Then third property we have is it must be normalized. Must be normalized, or must be normalized. It must be normalized, or we also call square integral function. Okay, so why what are these three things? Why our wave function must be continuous, my friends? Why? So let's say our Bohm, we have defined our Bohm approximation. Now we can understand all those three things very easily. So let's say this is your wave function. Okay, it has a discontinuity in this region, discontinuity, or this is also discontinuous because I went up, then I stopped there, and then I moved down. So such functions have a discontinuity because it is not a smooth function like this. It is a peaked function like this. So it has also has discontinuity at this point. So if you come from here, then the value at this point will be something else. If you come from here, the value of at this point will be something different. Okay, So this is the definition of discontinuity. Na? The right hand limit is not equals to left hand limit. It means that if you come from one side, it is giving different value. If you come from second side, it is giving different value. This is a definition of discontinuity. So if at one point we are getting two values of wave function, and wave function actually tells what is the probability of our particle to be there, then we will have the two values of probabilities. If I toss a coin, and what is the probability of head? One person says it's 50%, another person says 60%. This is not a physics. This is not physics. This can't happen. We need to have one value of probability at one point. So that is the reason that our wave function must be continuous. If it is discontinuous, then we will have a two values of two, or sometimes maybe infinite values can also be possible, because there are infinite directions also could also be there. In 3-dimension case, if you want, if it is a sphere, let's say, and there is a center of sphere, and you want to approach this center of sphere, then there are infinite directions to approach this center. Then there will be infinite number of values if your wave function is discontinuous at this center. So remember, wave function must be continuous, otherwise what is the value of probability to exist at that point, particle to exist at that point will be not unique. It will have many values. So if you understand first point, second point is actually very simple. It must be single value. So your function can't have such like, can't be like this, because at this value of x, the function has two values, this value and this. So if wave function has two values at 1x, it means it is telling you the two probabilities of particle existing at that point. That is also not possible. The same reason was there in our situation of what I am saying, our continuity. So first two are easily understandable. Now comes the third. In third, I would say that on this point, entire book can be written of quantum mechanics, and so many interview questions come from this point. I think you should open your brain and understand this point. So if I define phi, and if I, which is probability amplitude, and if I define probability, which is phi square, then the one very fun thing which I need is the sum of probabilities must be 1, because the maximum probability is 1. So let's say the probability of happening one event is 0.1, another event is 0.2, third event is also 0.1, so on. So if there are total 10 events, the sum of probabilities must be 1. It is a very simple probability theory everyone knows. Okay, so and you know, when the probability function is actually continuous function, or means not a discrete function, instead continuous, then we exchange our summation by integral. So simple thing is that phi square dx from -infinity to infinity must be equals to 1. This must be satisfied, because if it is representing probability, then sum of the probabilities must be 1, and this condition is called normalization. How please repeat, what is normalization again? That this condition must be satisfied. So let's say you have some function, let's say a sine kx, okay, and you take this integral, and you take this integral entire, and you are not getting a value which is 1, you are getting the value 4. Okay, so can't this be a wave function? It can. You just simply need to divide this entire function by 4. If you divide this entire function by 4 and again do this analysis, now you will get 1. Now you will get 1. So this is actually called normalizing the function. If you are given some function, and if you integrate that function, and you do not, and square and then integrate, you do not get the 1, but instead any other positive number, any number, even then that function is perfect. That function can be a wave function. You just simply need to divide whatever the value you are getting. So let's say if you are getting the value n, you just define your original, divide your original function by n, you are fine. Now my question, or not my question, but an TIFR, Hyderabad's question. This function and this function are the two different functions. So do they represent the same system or different system? Tell me. This is a one function, this is another function. So are they actually representing the same particle or different particles now? Tell me, anyone. Same. But how? The functions are different. Any MSc students? Should I tell you the answer?
They're different.
Different. Okay. So should I tell you the answer or you want to think about it?
I think in case first, a sin kx is equal to m, and in second, a sin kx is equal to 1.
Yes, perfect. You are right. But both are representing same particle and same state also. The reason is the quantum mechanics is very nice. Quantum mechanics says if you multiply your wave, please write this line on your note. If you multiply your wave function with any constant number, your wave function do not change. It still represents the same state of the same part. Hello, so I'm back online. Can you all hear me again?
Yes, sir.
Actually,
sir.
I'm sorry, here in Bangalore, it is raining very heavily. Karnataka is on, means what you can say, what is that alert? So it's raining heavily, so internet is little weak. So I am saying that wave function or the state of the function actually depends upon the form of the function, not the value. Okay, it actually depends on the form. Either it is sine kx or cos kx. It does not depend what is multiplied with it. So this thing you should remember. Don't go into too much deep that why. That is actually when you will get advanced in quantum mechanics, you will know the reason why. So normalization means dividing your wave function with any number does not change the wave function or does not change the physics you are dealing with. So with this, these three properties, if you are understood, now move to the second step. The second step was, so far we know that our phi is either a sine kx, a cos kx, or that third function inside the well, and it is 0 outside the well. And now we need to decide which function is okay, which function is actually perfectly fine with it. So first function to check is a sine kx. Second function to check is a cos kx. If you check these two, na, e raised to iota kx or e raised to minus iota kx is actually contained within these functions. Why? Because you know you can define your sine kx as e raised to iota kx plus e raised to minus iota kx. So you just simply need to check either your wave function is a sine kx or a cos kx. So for that, we will use the property called continuity of wave function. We just defined here your wave function must be continuous. So at x equals to 0, let me draw this wave function also here also. So wave function is 0 here, and we are looking for the wave function here, and wave function is 0. So if wave function is 0 here, then the value of wave function which is there must be 0 here, because if we come from here it should give you the 0 value. If we come from here it should again give you the value 0. So at x equals to 0, your wave function must be 0. So now tell me, out of a sin kx and a cos kx, which of this is actually satisfying? Either a sin kx is satisfying this condition or a cos kx. Your wave function
SI.
must be, yes, a sin. Your voice is not clear. What you're saying? Hello? Okay. So it should be a sin kx because your wave function must be continuous. So at x equals to 0, your wave function must be 0. So that is the reason that your wave function must be a sin kx inside. So now our problem is solved. It is a sin kx inside the well and 0 outside the well. K we know, we already have defined k square as 2me by h cut square. So k we know very well. Okay, but we do not know a. So how do we find a? We find the a by using the normalization condition, that phi square dx must give you the value 1. So if this is the case, let's do it. A square sine square kx dx equals to 1. Now I want you to tell me what should be the limit of this integral.
Zero to a.
0 to a.
Yes, because other than this limits, the wave function is 0. Okay. So if you solve this, actually, if you solve this, okay. So what is the value that you will get is, let's try to solve it. Quickly solve it and tell me what is the value that you will get. Okay, so solve it. 1 minus cos 2kx dx 0 to a. Solve with me very quickly. A, and this will give me the 0 value equals to 1. So your a will be under root 2 by a. How many of you got this? In this calculation, how many of you understood? How many of you do not understood that what has been done here? Okay, speak up, future IITians, IACians, speak up. Do you understood or not? Whoever is not,
Understood.
Yes, Bhaiya.
yes, yes. So a is under root 2 by a. So let's define the final phi a. So it is under root 2 by a sine kx inside means when x is 0 to a and it is 0. Otherwise, this is your. So what I said in the starting, that if you know the wave function, you know each and everything. So do we know energy? Do we know energy? So these are the different possible values of phi. Now tell me what are the different possible values of, means this is a phi. Now your k is 2me under root by h cut. So I said if you know the wave function, you know that what is the value of your energy linear momentum. But till this point, no one can tell me that what is actually the value of energy. What are the possible values of this energy? We know the k in terms of energy, but we don't know what is the possible values of energy our system can have. But that was a actual motive that is inside the well. You have find this, but whatever wave function, which we do not know, but we don't want to know, find this. We actually wanted to find what are the possible values of energy, my dude. Then how? Because one thing now we can do is apply another boundary condition, and that boundary condition, my friends, is phi is continuous, but it is also continuous at second boundary number 2. So phi is also 0 at x equals to a. Phi is also 0 at x equals to a, because other side of that boundary is also 0 na. So let's use this. So under root 2 by a sine ka must be equals to 0. Now there are many possible values of k for which this situation can be satisfied, because ka can be 0, k can be pi, it can be 2 pi, it can be so on so on. My only question to you is, so now let's just put the value of k, or we can just simply say n pi. Our ka must be equals to n pi, or our k equals to n pi by a. And what is k? K is 2 pi e by under root this n pi by a. So what is our e? It is n square pi square h cut square by 2m a square. And here n is equals to 1, 2, 3, so on. Do you all understand this calculation? Now I am coming to the physics, because let's first make sure that you understand the calculation.
Yes, sir.
So I need at least 5 or 6 yes before I move forward, because it's very important calculation.
Yes, sir.
Okay.
Yes.
Yes, sir.
So the very core question which is asked in the interview is, who gave you the possible values of energy? Does your Schrodinger wave equation gave that? No, my friend. The boundary condition gave you the possible values of energy. So who is actually deciding that what are the possible values of energies? Your boundary conditions. So boundary conditions actually define the systems of quantum mechanics. In classical physics, boundaries have a very less relevance. But in quantum mechanics, boundaries are extremely relevant. They define. And actually, it is a reason that your energies are discrete. Not the energy values are not continuous, my friend. Look at here. First energy value. What is the first energy value which is possible? Put the value of n equals to 1. So at that is pi square h cut square by 2 ma square. Second, 4 pi square h cut square by 2 ma square. So on. Okay. So energy levels are discrete. Discrete possible energies are there. I hide the fact very well here that why n is not 0 and why n is not negative here. In this entire calculation, I could have said that Ka is 0, but when I defined this n, I didn't say that n is 0. Why I did this? Why I did this? I deliberately did this, because the most book do this and they do not tell you the reason, and that reason is asked in different exams and in interviews, but I am here to tell you that reason. Let's say n is 0. Let's assume that n is 0, or let's take that n also 0. What will be the value of energy, my friend?
0.
Energy is 0. So what will be the value of momentum, my friend? If energy is 0, what is momentum?
0.
0. So momentum is 0. Now comes the uncertainty principle, my friends. Delta x delta p must be greater than equals to h cut. If p is 0, what is your delta x? Infinite. But your delta x can be within 0 to a only, na? Your particle is only within 0 to a. You don't know where it is. So maximum uncertainty can be a. because you do not know within this A region where it is. So maximum uncertainty can be A, but if your momentum is 0, it comes out to be infinite. So this is a reason to make sure your uncertainty principle holds. Your n cannot be 0, because if n is 0, energy is 0. If energy is 0, momentum is 0. If momentum is 0, uncertainty is x is infinite. So how many of you understood this? How many of you will be able to answer this question in interview? Why n cannot be 0? This is a direct question which is asked in the interview. So do you all understood? Very nice. Now the second question comes, why n cannot be negative? My friend, look at this k. Look at this k. Do you think this k can be ever negative? Can under root give you negative value? Tell me. Can under root give
No,
you
sir.
negative value? Never. Under roots never
No, sir.
give you negative value. So if under roots never give you a negative value, h cut is not negative. So why k? How ka can be negative? How ka can be negative? Because a is positive, na. So if k is negative, it means k is negative, but k can never be negative. So if k can never be negative, that is why we also ignored the negative n's. So the only possible values of n are 1, 2, 3, 4, 5, 6. So how many of you have the crystal clear idea why n is 1, 2, 3? So very important, because this you can study in infinite potential than anywhere. You can qualify jam with this anywhere. You can qualify gate with this anywhere. But this will make you bring to the IIC either, because you have to give the interviews. Okay. So now move forward. Yes.
Sir, how delta x is infinity if delta p is 0?
Okay. So if delta, okay, what is this? So if I put delta p 0, then what will be delta x?
Okay, sir.
Yeah. So that is simple
ठीक है.
mathematics. Okay. So now let's move forward. So what we have said is we have actually solved the problem. How we solve the problem? We said our system, our particle can have the energy values n square, pi square, h cut square by 2ma square, and correspondingly the wave functions are root 2 by a sine n pi x by a, n pi x by a. Why I said this? Actually it was kx, okay, sine kx, and we just said that k is n pi by a. So I just put the value of k here, nothing else. So I have not done anything difficult. So these are the possible values of energy our particle can have. It is if it is contained inside the well, and if the particle has energy En, then the state of the particle is phi n. Which state? Energy eigenstate. These are actually energy eigenstate. So I will stop till here. But remember, this is not finished. I want you to look at this lecture 3 times at least, because if you will not see this lecture again, you are going to forget everything, and it is not my responsibility, it is not my teaching skills, because no book can cover everything which I have covered in one lecture. So watch this lecture 3 times, and tomorrow we will forward build on this, because abhi to bhai shuru hua hai, it's just beginning. Let's see how I will pull up at least 10 more physics concepts from here, and all of them will come in the exam. And then in third and fourth lecture, we will actually solve the problems based on this, and then your quantum mechanics will be perfect, and then you will be able to solve any quantum mechanics. At least you will have a very strong foundation of the quantum mechanics. So best of luck. Tomorrow we will start from here. So I think let me just stop the recording, and then we will take the questions.